Okay, so we're going to talk about the domain and range of functions and also talk about special functions called a piecewise function. The domain of a function can be described explicitly or it can be implied by the expression used to define the function. The implied domain is the set of all real numbers for which the expression is defined. When an input is substituted into the expression, which results in the expression not being defined or not a real number, we say the value is not in the domain of the function. Okay, so let's look at this example here, which asks us to find the indicated values and determine whether the given values are in the domain of the function. So our function is 1 over x minus 3, and we're asked to find f of 1 and f of 3. Okay, so let's plug in f of 1. So we got 1 over 1 minus 3, which gives us 1 over negative 2, or to make it look pretty, negative 1 half. Put the negative side in front. Okay, so then negative 1 half results in something that's defined, right? And so we would say negative 1 half is in the domain of f of x. All right, f of 3. F of 3 is equal to 1 over 3 minus 3, which equals 1 over 0. Now, this is an undefined expression. If you took a calculator and took 1 and divided by 0, you get something undefined. Okay, so in this case, 1 over 0 does not make sense. It's undefined. Therefore, 3 is not in the domain of f of x. All right, let's take a look at b here. We have the function g of x equal to the square root of x plus 5. Find g of 16 and f of negative 7 and determine if those inputs are in the domain of the function. Okay, so g of 16 is the same, is equal to the square root of 16 plus 5. Well, the square root of 16 is 4, so 4 plus 5 equals 9. And so 9 is in the domain, since it's well defined. Okay, so 9 is in the domain of f of x. Okay, we have, and I notice there's a typo here, that should be g. Let's cross that out. G of negative 7 is equal to the square root of negative 7 plus 5. Well, the square root of negative 7 results in a complex number or imaginary number. And so since we're only talking about real valued functions, negative 7 is not defined for real numbers. So this is not a real value. Okay, and so negative 7 is not in the domain of f of x, or in this case, sorry, g of x. I have the habit of always calling a function by f of x. Okay, so when you're looking for the domain of a function, especially when you're given an expression or equation that represents the function, you want to watch out for things like negatives under the square root. Okay, so the radicand, right? That's what we call the expression under a radical, especially an even radical, even index radical. You always want the radicand to be positive. One other thing you're looking for as well is if you have a fraction type of thing, okay, whatever the expression is on top, it could be like 2x plus 1, but whatever the expression down here is, we don't want the denominator to be 0. Okay, so denominator should never be 0. Okay, and the values that make the denominator 0 will will make your function undefined. Okay, so really right now we're only looking for things like even index radicals where the radicand can be possibly negative, so we want to exclude those values. And anytime we have like a fraction type of function, then we want to make sure the denominator is never 0. All right, let's look at some examples. Find the domain of each of the following functions. So we have f of x equal to 1 over x minus 3. Now notice we have a fraction. We want that denominator to never be 0. So let's figure out where it's 0. Okay, so we need to solve an equation essentially. So basically set the denominator equal to 0 and solve. So set denominator equal to 0 and solve. 2. Exclude any solutions to part 1 or step 1. Okay. And all right, so the idea is, okay, well, I set x minus 3 equal to 0 because that's the denominator. Now, solving that equation by adding 3 on both sides gives me x equal to 3. Well, this is a bad value because when I plug it in, I'm going to get 0 on the denominator. So we need to exclude it. So the domain in set builder notation would be the set of x such that x is not 0. Or in interval notation, this is the set of real numbers, negative infinity to positive 3, but excluding 3, so we use a closing parenthesis, and then we have the union, open parenthesis, 3 to positive infinity. Okay, so that's the domain for this function. Part B here, we have a square root. And once again, what do we want to do? We want to basically make sure that we don't get negatives under the radical. So the radicand, so step 1, so we got to solve the radicand, figure out where it's positive, and that means or 0. So we want to figure out where the radicand is greater than or equal to 0. Okay, what's the radicand in this case? 3 minus x. It's whatever is under the square root symbol. Okay, so we have 3 minus x greater than or equal to 0. We're going to subtract 3 on both sides to get negative x greater than or equal to negative 3. And then we're going to divide by negative 1 on both sides. Doing so will give me x less than or equal to positive 3. Okay, so these are good. These are the values that will make the radicand greater than 0 or equal to 0. And so that's going to be our domain. So the domain then for this function in set builder notation is the set of x, or real numbers x, such that x is less than or equal to 3. Or in interval notation, it will be negative infinity, open parentheses, negative infinity to positive 3. And so since we can include 3, we put bracket, our closing bracket. So the domain is the set of real numbers such that x is less than or equal to 3, or in interval notation, negative infinity to 3, closing bracket. Okay, so the next function here, we have a fraction. And once again, the denominator is x squared plus 2x minus 3. We want to know where x squared plus 2x minus 3 is 0. Okay, so we need to figure out where this happens. Okay, so then we'll solve this by one of the techniques we've learned. I believe it factors. So we'll factor this as x plus 3 times x minus 1 and solve that equation. So using the 0 factor property, x plus 3 is 0 or x minus 1 is 0. And so solving both of these, we would have x equal to negative 3 as one solution and x equal to 1 as the other solution. So these are the bad values, the values we want to exclude, which makes the denominator 0. All right, so then the domain here then, in set builder notation, is the set of x such that x is not equal to negative 3 or x is not equal to 1. Okay, so it can't be either one of those values. All right, so in interval notation, it's a little bit more tedious to write, but it would be negative infinity to negative 3 closing parenthesis, because we don't want to include negative 3. Then use our union symbol, open parenthesis, negative 3 to positive 1, closing parenthesis, another union symbol, 1 to positive infinity. Okay, so it's a union of intervals. So those are every value in those interval, or in that similar set there, is part of the domain. D here. Here we don't have a fraction. We don't have square roots. We have an x cubed term, or power function if you want, or the absolute value function. And there you're not going to run into the issue of taking the square root of a negative number or dividing by 0. And so basically, any input you get, you're going to get the input raised to the third power plus the absolute value of the input, and then you're adding those values together. Nothing could go wrong here. You're always going to get a real number out of it, and everything's well defined. So in this case, it's all real numbers. The domain is all real numbers. Set builder notation, there's not really a way to write that. We might some books might use, or textbooks or authors might use, say, this symbol to represent real numbers instead of real numbers, like a boldface R. In interval notation, though, that we could express that as negative infinity to positive infinity. Okay, so that's how you find the domain of a function when it's expressed as an equation or an expression. All right, you can also find the domain and range of a function visually. The graph of f of x is given, find the domain and range of f of x. All right, so if we're looking for the domain, basically you want to kind of trace out the function as it goes from left to right. And I want to point out that on this end here, you have an arrow indicating that it's indefinitely going this way. Okay, even though we don't see it, it's indefinitely going that way. So if I trace this graph from left to right, we need to observe what's going on. What are the x values being attained as we go from left to right? And technically, as we're tracing, you can see that the x values are being attained going this way, and then stopping at 5. So you notice, since I'm going from left to right, if you project, you can see that project onto the x-axis here, all the x values are being attained up to 5. Okay, but keep in mind though, this was going all the way down still. So technically, way over here, negative infinity, as you come from left to right, you're achieving those values. And so the domain for this function would be negative infinity to 5 bracket in interval notation, or in set builder notation, the set of x such that x is less than or equal to 5. All right, so the y values, or the y-axis, horizontal axis, vertical axis, would be, we got to pay attention to which values are being attained on the vertical axis. Okay, so as we trace the graph from left to right, what values are being hit on the y-axis? Sometimes they repeat. So if I'm coming down here, I'm hitting everything on this part of the graph. Everything going up, right? Going up, going up, going up, but then I reach a peak. So it's going up, going up, going up, and then it stops. And as I go down here, these values are repeating until I get here. And then I keep going up this way, these values are repeating. And then I get stuck at 2 because it's going horizontally, it's not changing y. And so what you see is the values basically going this way all the way up to that peak up here. Okay, so once again, let's go over that again. As I trace the graph from left to right, project onto the vertical axis. In other words, follow it to the graph as you go from left to right. And it hits there, but then as I come down here, now it's still hitting these and repeating again. And I get down here, and these guys are getting repeated again. And then it stops and gets stuck here. Okay, so all the values being attained is what I drew in blue there. And so the range of this function is going from negative infinity to positive 4. And it looks like it attains the value 4. Right? In other words, once again, the arrow here means it's going indefinitely this way. Okay, down. So you're getting all those bottoms, all those y values or values on the vertical axis all the way from negative infinity up to 4. Okay, so the next thing here is we're going to graph each of the following functions and then estimate the domain and range of each. To graph f of x equal to x plus 4, it's probably best to use a table of values. Okay, so I might have an x and then I have a y to get a feel. And you could try plugging in something like, say, negative, say 5, for instance, but you'll realize that once you plug in negative 5 there, you get the square root of negative 5 plus 4, which equals the square root of negative 1, which is not a real number. And so it's not part of our domain. Okay, so if I plugged in negative 4, I would get the square root of negative 4 plus 0. Sorry, negative 4 plus 4, which gives me the square root of 0, which is 0. So we got a little pair there. If I say plugged in, I don't know, negative 3, square root of negative 3 plus 4, we get the square root of 1, which is 1. Okay, so you can keep on doing this and get some values. I'm going to go ahead and be a little bit quicker here by using decimals. If I could find it. Okay, so let's go ahead and use decimals. All right, so once again, f of x equal to the square root of x plus 4. You can see we got value. And remember, I showed you there's a way to create a table. If you click on that little gear icon, we could create a table and put values. And so just to double check the values we got here. So for instance, if I took negative 5, you can see that we get something undefined. Of course, if I took negative 6, something undefined. Negative 7, undefined. Negative 8, undefined. Okay, so we see that our first value in our domain as we go from left to right would be negative 4. Okay, and then we already tried negative 1, or we didn't try negative 1, but we tried negative 3. We could try negative, say, 2, for instance, negative, 1, so forth. Okay, and you can keep on doing this as many times as you want to generate some values. Okay, if you notice, I'm looking up for all the values that are giving me nice whole numbers, which way makes it easier to plot. Okay, so you can see that all the x values that are allowed are basically greater than negative 4. Let me go ahead and plot this real quick. So negative 4, 0 would be a point. Negative 3, 1 would be a point. And then I'm going to use 0, 2. And then we have one way out at 5, 5, 3. And the graph looks something like this here. Okay, and so if we look on the graph, and I'm going to zoom out, you can see that it's obtaining every single value to the right of 4, as an input. So as an input, any single value to the right of 4 is looking like the domain. But if you keep on going out and out, you see it's increasing slightly. And all those y values are getting bigger and bigger. Not very fast, but they're getting bigger and bigger and bigger and bigger and bigger. And so you can see that the range is getting big all the way to positive infinity. But where did it start? So let's go back. Let me hit the home. So give it the default view. So the first y value that we see as we go from left to right, was 0 here, right? 0, and then those y values, steadily increased. Okay, so what does this give us? So let's go back to the notes here. What does this give us? Well, this tells us that the domain, and I'm going to write this in interval notation, is bracket -4 to positive infinity. And the range is bracket 0 to positive infinity. Okay, let's take a look at another example here. Once again, here we shouldn't have too many issues in terms of what inputs to put, because we don't have a square root or a fraction here. But let's see. Let's just compute some y and x values. Okay. For instance, sometimes when there's no issue about domain, really, you can see that since we don't have a square root or a fraction here, it's probably okay to take some values to the left of 0 and to the right of 0, and even 0 itself, and see what they become. All right, so we have -3 cubed minus -3, right? That would give us -27 plus 3, so that's -25. -2 cubed minus a -2, so that gives us a -8 plus 2, so that gives us -6. -1 cubed minus a -1 gives us a -1 plus 1, which is 0. 0 cubed minus a 0 is 0. 1 cubed minus 1 is 1. Excuse me. So not 1. 1 cubed is 1. Minus 1 is 0. 2 cubed. 2 cubed minus 2 gives us 8 minus 2, which is 6. And 3 cubed minus 3 is 27 minus 3, which is 25. You can see some symmetry here in the terms of the numbers coming out. But in any case, what do we see? Well, -25 is off my grid, but let's go ahead and look at -2, -2, -6. So we have value here. And then -1, 0. Oops, sorry, -1, 0. I'll put 0, 0. -1, 0. And then at 0, 0, 0 again. And 1, 0 again. And then at 2, we get 6. All right, so before I connect this, it's probably best to include more values here, because if we connect the dots here, it might look something like this. And that's not how this graph looks like. And so let's go ahead and use Desmos to try this again. All right, so back to Desmos. I'm going to go ahead and refresh this page here by leaving the page and see refresh. All right, so I'm going to type in my function f of x equal to x cubed minus x. All right, I already generated a lot of x values, but you could keep on generating x values if you choose. But here you see that actually peaks a little between -1 and 0, and then at 1, 0. Oops, right? These values here are very important. You notice how it's peaking there. So if we conclude the graph there, we see that it goes up a little and then down a little. All right, so how can we find the domain and range here? Well, once again, as I've looked at the equation, we looked at a similar equation earlier. We have a power function, x cubed minus x. And so we know that there's nothing going to go wrong by dividing by 0 or taking the square root of a negative number. And so so this makes sense that there's going to be, the domain is going to be from -infinity to positive infinity. And so just to quickly show you here, I mean, if we plug in, say, a value, say like -1/10,000, you see that it's a huge number, or -100,000, excuse me. It's a huge number. If you do the same thing for x values, oops, positive, say, x, right, you can see that it's going, for inputs that are, pretty big as well, it's going to positive infinity. The y values, you can see that it's shooting up all the way to positive infinity and shooting all the way down to negative infinity. Okay, so let's write down what the domain and range is. So the domain is going to be in interval notation, -infinity to positive infinity. and the range is going to be from negative infinity to positive infinity. Once again, trace the graph from left to right, and notice your y values are getting as small as you want and as big as you want. All right, next function here. We have f of x equal to 1 over the square root of x. And once again here, we're just going to take a, by the way, let's complete the graph for this one here. All right, so just so we have it in our notes here, it looks something like that. And then shoots up. All right, so the next function here is 1 over the square root of x minus 2. Notice we have an issue. We have an issue that we have a denominator, right? So we can't have that equal to 0. And then we have a square root. So the square root has to, we have to exclude any values of any inputs that make the radicand negative. And so clearly, if you look at x minus 2, greater than or equal to 0, this can happen at 2, right? So we know that we're gonna have, that would make everything, any input greater or equal to 2 will make the radicand positive or 0. However, we're going to have an issue when x equals 2 because then the square root of 2 minus 2 is 0 and we'll be dividing by 0. So if you did a quick table here, you would probably not want to start less than 2. Okay, so we would start at 2 and then maybe 3 and then 4 and then 5 and so forth. Let's go ahead and use decimals to get some y values here. All right, let's go ahead and use decimals here. So let me get rid of this function here. And then we have 1 over the square root of x minus 2. And then get rid of that and then generate a table value. So you can see it's undefined, but we'll, right? And you can see it's still undefined at 2, but then after 2, say 3, then 4. In fact, it's undefined at 2, but we know that it will make sense for like 2.1 or 2.05. Okay, stuff like that. So you can see that we're generating, intermediate values here and stuff like that. But I want you to see some behavior. The behavior of the function as you're going to say positive infinity and as you're getting closer to positive 2 from the right. So let's pay attention closely here. Okay, so we know it's undefined at 2. We've seen that already, and anything to the left. So we'll pay attention to x values, right? We know that x has to be greater than 2. And so if I look at 2.001, notice the y value is 31.62. What if I change that y value to say 2.0001? It got bigger. Okay, so it seems as you're getting closer to 2, the y values are jumping. Okay, so we know that at least from the, if we examine here, as you get closer to 2 from the left, from the right, you see that it's shooting up here. It's shooting up. And this is something called an asymptote, which we'll talk more about when we talk about rational functions. But so this line here would be 2, but if you follow this graph all the way up, it's getting, the x values is getting closer and closer to 2 from the right, but then the y values are getting bigger and bigger and bigger and bigger. Okay. However, contrary to that, let me go back to the poem view. If you look at the y values going this way, you see as x gets bigger, the y values are getting very small. Getting smaller and smaller and smaller and smaller. In fact, they're getting close to 0. And that's called a horizontal asymptote. However, we'll talk a little bit more about that in a later unit. All right, so what have we pretty much observed? That we're basically bounded above by the horizontal axis, the x-axis, and bounded to the left if we took a little vertical line, x equal to 2, going up and down here. And so the domain for this function will exclude 2, as we've seen, because that's dividing. Well, if we plug in an input of 2, we get denominator 0. So it'll be 2 to positive infinity. As you saw, as we move from the graph from left to right, the x values made sense. Okay. Range, we saw that it was bounded below by the x-axis. Does it ever get to 0? In fact, from the graph, you can see that it's getting pretty close to 0, but never achieves it. And so we know that the range would have the smallest y value maybe could contain with 0, but it won't, because you would have to be able to solve this equation, and you can't. All right, so we'll exclude 0, and it seems as if I follow that graph all the way up, that it's going to positive infinity. All right, so the quick sketch of this, we had some points. For instance, go back to the table. You solve a bunch of points, but I'm just going to give you a rough idea. So we had a point that's one of the y values. We had 6.5. So 6.5 is right about there. And then something pretty close to say, let's try 2.0. Plug in 2.5 into the graph there. 2.5 for x would be right there, and that would be about 1.14. So right about here. Okay, and we saw that it kind of like shot up pretty steep this way, and then as it went this way, it kind of get flat. All right, next function here. Once again, generate some points. The good news here is that we don't have a square root function. We don't have a fraction function. And so we don't have to worry about dividing by 0 or taking the square root of a negative number. So this one appears the domain just by what we learned by interpreting the expression. The domain is going to be negative infinity to infinity. What's not clear though is range, and we'll examine that right now using decimals. Okay, so let's go ahead and graph in decimals here. All right, so I'm going to get rid of this function here, and then type in x to the 4th minus 2x to the second power minus 3. This looks pretty cool. Once again, if you plug in some arbitrary large x values, so we'll say negative 2,000, you see it's already exploding up there. How about 200, even getting pretty quick as well. Negative 20, if you plug in an input of negative 20, you already have 159,197. So you see that the x inputs that are arbitrary and small in the negative direction, right, give you very large y values. And that's indicating, and that's clear too, just by the fact that this graph, as I trace from left to right, it's shooting way up. If I go all the way to the left of this graph, the y values are getting pretty big quickly, and you can just verify that by plugging in some negative x values. And then likewise, the same thing's happening over here. Those y values are getting arbitrarily big as well as you plug in y values. I'm barely at, not even for an input of 4, and I'm already beyond 8 point something. In fact, I can't even see it's off the graph, right? Zoom in, you can see that it's skyrocketing up there. However, if you look at the y values, they seem to be going upward, right? In other words, the y values seem to be greater than or equal to negative 4. Okay, so it looks like it's hitting a bottom of negative 4. And so that tells us that the range is basically going from negative 4 to positive infinity. Negative 4 to positive infinity, and we include negative 4, so I'm going to put a bracket negative 4 there. And using decimals here, we saw that we have a point at negative 1, 4, and positive 1, negative 4. And then one of the characteristic points here was at 0, 0, negative 3, which is called the y-intercept if you recall. And then we had, say, an x-intercept at negative close to negative 2, close to positive 2. And the graph looks something like this, and it shot up pretty quickly this way. And it came down and around, and then shot up again. All right, so it's a pretty interesting function there. Domain is from negative infinity to infinity. Range is from negative 4 to positive infinity.